get right into it instead of me thinking and talking a lot. So today we're doing Resistance, the Final Frontier. And we got office hours afterwards. I know a lot of you are asking lab questions. I really appreciate the hard work, and I truly hope that benefits you guys in your careers, all the hard work you're doing. And I believe it will. So thank you. That does not go unnoticed that you guys work so hard on this measly little 10-point lab assignment, but it's good stuff for your careers, and let's leave it at that. I'm going to start today by looking at share, and then I'll start talking about it. So we're going to talk about resistance all day today. Hopefully that gets more people in here. Okay. All right. So there's 26.13. Looks like a cigarette, but it is not. All right. So it looks like we got a piece of carbon here. Attached to a piece of what? Nichrome? Your favorite? Nichrome. I have no idea which ones. Do it like this. And then we're told the lengths. Oh, we're not told the lengths. The lengths are labeled, and it looks like, so this is an interesting problem. I just want to point something out. Normally, when a variable is given in a problem, we assume it's a known. In this case, look, we're told numbers here. So everything's got, no, oh, that looks like I need to do an exponent there, but you get the idea. So it looks like we've got a bunch of numbers given to us. So notice these are not given. We don't know the L's. And it looks like we don't know the resistances. These are not radii. Okay, so I'm using little r for the radius here. Oh boy. All right, and sig figs are all over the place. Let's not worry. And our goal here is to determine L1 and L2. Okay. So we know the combined resistance is 10. And we could be lazy with sig figs here, all right? We know the givens were, the resistivities were given, the alphas were given, and the basically the radius or the area is given. So those are the givens in this problem. That's what we know. The rhos, the alphas, and the R. I think if I read all that right, I'm just going to check one last time. The rhos, the alphas. Okay. So now I'm going to open this up to you guys. Maybe for once, try not to look at the solutions right away. If you've already looked at the solutions, oh well. But what do you think? Any idea? I gave this question on a test once, and it just snowed everybody. So if you're feeling kind of like, what? But I'm curious, let's maybe try and get a dialogue going. Maybe tell me what you think might be a good way to start. Any ideas? We're trying to figure out the lengths. Any equations I might write down? Anything?
You need to replace R1 and R2 with the equations that you can get area from.
With the end of that cutoff.
Where you can get area?
Yeah, okay. So I think he's saying do this.
Yeah.
Right? Yep. That sounds like a good idea to me. All right. And then how do I get the radius involved in here, right? So you're probably okay. Do both of these have the same radius? I think they do. It looks like it. So I'm going to just get lazy here and just write pi r squared since they have the same radius. We could tell that because they're abutted end to end and they look the same. So there's the area. All right. And we can put that into here. So now we have one equation, two unknowns, right? So Nick's in the clear. He contributed. How could I get another equation here? Any thoughts? You may have to reread the problem statement to see. In particular, it says, this resistance is designed to be unaffected by temperature change. How could I get an equation out of that?
As the resistance of one changes higher, the other one lowers to match it.
Okay, so what would the total change be?
0.
So how would I write that in an equation? The change in resistor 1, how would you say it?
Equal and opposite.
Yeah.
Okay, so you're saying that equals negative the change in R2?
Yeah.
That's fine. You could also just say like delta R1 plus delta R2 equals 0, which is what I was thinking, which gives you this. Same thing, right? Outstanding. All right. So now what would you do? How can we get this involved? What's the equation?
Would you mind explaining a delta R1 plus delta R2 is equal to 0?
Yeah, so the problem says as you heat this resistor up, the resistance shouldn't change. So that's the equivalent to a change of 0.
Oh, okay, I get it.
Yeah, all right. So now I'm going to go to, remember all these formulas were on some page. We have like a cheat sheet of all these formulas. On mine, it's page 105, yeah. And so I've got this now. There it is. This one would be alpha 1, R1 naught, delta T, and we have to remember here, in this case, what does this R1 naught mean? What does that subscript 0 mean for resistors? Do you remember?
Is it the initial, well, not, is it the initial resistance before like it's heated up, like before the temperature changes? Or
Okay,
like
and what is the standard temperature for resistors?
20 degrees Celsius or
Yeah.
room temperature?
I hope you guys remember that on quiz day. Remember that resistance, this is a common mistake people make. I see it every year. The standard temperature for resistors is 20. Okay, it's not 0. So even though it looks like 0, it means 20. So this is the resistance of number 1 at 20 degrees Celsius. Okay, I warned you, I can't do any more than that. Okay, which one of these things is heating up more?
Neither.
Exactly. Now, there might be temporary dissimilarities in temperature, but we're going to assume that as this thing runs current through it, they're both going to heat up and it's going to be at approximately the same temperature all the way throughout. That's not perfectly true for instantaneous changes, but it's approximately true. So if you leave this thing running for a while, it is true. We're going to assume these two are going to be at roughly equal temperatures. That means, what can I do with this temperature change?
They're the same.
Drop it out. And then, now what should I do? I guess I could plug in that this is that, right? And we've got two equations, two unknowns. You're off to the races. Right? So here's one equation that's going to have L and L in it. And here's another equation that's got L and L in it. From there, it's an easy problem. So I actually got this out of the Physics 142 book, and I gave it to my 163 class, and they all failed. So I'm like, okay, I better give this to everybody. It's a surprisingly sneaky question because of that delta being zero trick. So yeah, you got to be able to read the problems and do some critical thinking there. And that's a sneaky one. So I like to do that. So that's a good warm up for us today. The moral of the story is this. Sometimes you want to use the delta R equation. Sometimes you want to use R as a function of temperature is equal to R naught times 1 plus alpha times delta T. And then remember, this is always T minus 20 degrees Celsius. So there's kind of the summary of these types of problems, what you got to look out for. All right, so the standard temperature is 20. You're expected to know that for resistors. If you don't, you're going to lose points. And then in some problems, it's easier to use delta R. In some problems, it's easier to use R as a function of temperature. And remember that these temperatures are in Celsius. That's about all there is to say about that. But there is one more thing. Let's check it out here. Okay, so when you do that problem, you figure this all out. Let's look at this bonus and think about this. This is how you would want to, this is kind of an engineering question, right? Suppose we want a similar wire. We want it to be 10 ohms. And we want it to be independent of temperature with carbon and nichrome in series. So the same exact thing, except we want this wire to be 100 times shorter. Could it be done? If so, what problems might we have? What do you think? Any thoughts? And try to maybe do it without looking at the answers. It's kind of a fun question. If you want this wire to be shorter, but give it the same resistance, what do you have to do?
I literally have no idea, but would you squish it?
Say again, would you what?
Would you like squish it to make it so that the area
Yes,
of it, the
that's
cross-sectional
it.
area is really?
Yeah,
Oh.
that's it. So you would have to use smaller area, right? So how much smaller would you need to make the radius?
100 times smaller?
Nope,
Oh,
It's squared, so it's going to be some proportion.
because it's R squared. Gotcha. Right. So if you make the radius 10 times smaller, the area would be 100 times smaller, right? I hope you, yeah. So you're right. We need to make the area 100 times smaller, which means the radius. So I had asked about the radius and maybe you were answering about the area. So my apologies. But yeah. So think about this now. What problems are you going to have? 0.2 millimeters of carbon. Do you guys know anything that looks like that? Maybe
Like pencil lead.
exactly. In an online class, this is a dangerous question because no one would ever get it. But yeah, back when we used to use pencils in the real world, pencils, the smallest pencil lead is usually what, about 0.5 millimeters? And they break all the time when I use them. But yeah, so just imagine trying to do this with a 0.2, and that's graphite, right? That's carbon. So yeah, anyways, that would be very difficult. All right. So that's kind of a fun warm-up question. All right. Any questions about that before we go on? All right. And you could put it in the chat or you could ask or whatever you want to do. I'll catch up if I'm cutting you off too soon. My apologies. Okay, so there's one you could try on your own. This is talking about two resistors in parallel. So notice this is something we're going to allude to at the end of class. When you put things in series, the resistance just adds up because you're basically just making a longer tube. There's more drag. Okay, when you put things in parallel, you get the 1/over rule, which, if you care, there that is. We're going to discuss that more in the next chapter, maybe at the end of today. All right, so there's another variation you could try and see what happens with this one. Okay, so it's a variation on that problem to see if you actually know what you're doing. This is a good problem to read. I would read it before you turn in your lab report. Maybe that makes sense. Okay, here's a nichrome wire. This one, maybe you guys might want to take a look at these before you turn in your lab report, just to kind of see if you learned anything from the lab. Okay, and then why don't you try and think about them and draw what you think. It's a quick sketch, and then look at the solution, and then use that to double check your work in your lab. All right, and this is a good one. This one has a bunch of numbers in it, so you could check that. I do want to point out one thing. See this one, Q equals MC delta T. We haven't used that equation before. So this is a physics 162 equation. What that means is this is not on a 163 test, since some people haven't had that yet. But if you want, you can do this problem and just use that equation. I thought this would give you a better feeling for the numbers, just realistic numbers, okay? So I'm going to leave that for you to do later. All right, let's get rid of those drawings. All right. And now we're up to the last piece of this one, your favorite, calculus. So some people love it, some people hate it, whatever. The idea is, you know that if you take a chunk of wire here, and then another chunk of wire here, and I call this R1, I'm going to do this on the whiteboard. This is going to take me a minute, so. It's basically like this picture right here. Let's say we have some segments of wire here. And let's just start with 3. So we got R3, R1, and R2. From experience, for 13, what's that? Oh, that was one of the equations from page 105, Luke. That was one of the equations from page 105. If that didn't make sense, I'll address it after this one, okay? Cool. All right, so let's say we have 3 resistors here. Well, these resistors are coming one after another. They're in series. So it turns out in series, you just add them up. R total is equal to R1 plus R2 plus R3. Nothing crazy. Well, now, in general, isn't that a lot like the sum of R sub I from I equals 1 to n? It is. Okay, thanks, Luke. Okay. So, and yeah, I appreciate that. So wait, sums, isn't that the same thing as an integral? It is. So you could think of, I guess I should have written this way so it looks the same. So now it's starting to look pretty similar. I add up these 3. That's the same as adding them up. That's the same as doing an integral over a continuous distribution of resistance. All right. Now you might be saying, this is silly. Who would ever do a resistance calculation this way? Well, it turns out this is probably not absurd to think about, especially for an electrical engineer, because what do you do in electrical engineering? You're going to take a wafer like this, and you could draw patterns on it. And you could vary the size of the thickness and you could basically make any shape you want, and you can implant ions, and you could do things and change the resistance. You could do all kinds of things and have a variable resistivity, and you could have variable areas. And so because that comes up in here, it's very plausible that we're going to have, let me try and write it the same symbols I used in the book. Did I use DS? Yeah. When you're making semiconductor electronics, it's very plausible that you're going to change the resistivity as a function of space. This happens in the real world, or the area of a wire. Or you could even use this to calculate what happens if you have a wire that's tapered or something that because it got put under stress, or maybe you deliberately did that as a design feature. But yeah, so it's possible that either the resistivity or the area here might change as you move around. And so how could we handle these types of problems? Let's try and do this procedure. And there was a question there, maybe. Did somebody want to chime in with the question?
I was just wondering what a wafer is.
A piece of silicon that's about a micron thick.
Got it.
Yeah. So it turns out, if you've ever seen this, chips are made on what's called an 8-inch wafer. There's 2-inch, 4-inch, 8-inch wafers. And so a typical size, and it's maybe like 1 micron thick. And sometimes what you do is you get sapphire, which is aluminum 2, oxygen 3. And so basically aluminum, oxygen makes these beautiful gemstones, right? But yeah, it isn't ruby and sapphire the same, I think. I forget, but anyways, you take some aluminum oxide, which is maybe a millimeter or 2-3 millimeters thick, and then you can grow this on top of that. Okay. And so there's different, we could go all day on that. A wafer is just a piece of raw semiconductor material that's very thin. Wafer thin. All right, there we go. All right. So now let's take a look here. Let me go back to the screen share. The principle is easy enough. You just add up all the resistance in series, but you have to use an integral. Now look out. Let's look at this set of bullets very carefully. You should only use this formula if something is non-uniform. Otherwise, why would you do this? Right? Why use calculus? Sorry, I forgot. Oh, it looks like I left out the period on all. That's a style thing, I guess now. Whatever. Now, to use this equation, we need to get the resistance of each shell, right? The shells have to be designed, or you need to split up the problem with calculus such that your shells are cross sections, right? So that current flows through the area of the shell. All right. The thickness of the shell is like the length of the resistor. And usually rho is uniform. If it's non-uniform, I'd give you some formula. Now, like I said, there are cases in the real world where rho would be non-uniform, semiconductor wafers. All right. So let's try and take this information and these bullets. And I want everybody to think about this question. All right. And remember, the first thing you do you really need that equation or not? Check that first. If you don't need it, do rho L over area. If you can't do that, then do the integral. Okay. So I'm going to look at 26.18 and draw it up. inner radius A, outer radius B, resistivity. So now we're back to this one has no numbers in it. So because this problem has no numbers in it, I'm assuming these are all knowns. So in this case, we're assuming that the length and resistivity A and B are all given. Okay. So that's what I've got. What do you think? Do we need to use calculus for this first one? What do you think? Yes or no?
No.
No. Resistivity is a constant. Excellent. Good job, everybody. And look, as this is flowing, the cross section's not changing. So then this one's a no-brainer. R equals rho L over the area. In this case, the area is going to be pi times what? B squared minus A squared?
Yeah.
Oh, old blue. Looks like time for blue to hit the highway here. Money. All right, so that was easy. That beats doing calculus. What if we go to case 2? If you go to case 2, is the cross-sectional area changing?
Yeah.
Technically, yes. Yeah.
Yeah. So then we have to do calculus. And then I'm going to need the whole board here. So I got to erase this one. Case 1's pretty easy. It's okay you could use the solution for that. It's looking kind of good. Okay. So current is flowing radially outwards. So in this case, what are my shells going to look like?
Pi r squared.
Nope. Like that, right? The current's flowing through that glass
2 pi r dr.
outwards. So, right, if you think about it, the current's got to flow out through this. I wasn't just chugging to annoy you guys. I needed the demo. All right. So, right.
Is the
So
resistance function of R then?
Is the what?
Is the resistance a function of R?
Resistance is effectively a function of R here, because let me ask you this. I'm going to draw 2 random shells here. So actually, let me just draw this shell first. Let me draw one. Okay, now if you look at this current has to flow through there. If I could try and draw the perspective, that green shell actually looks like this, right? And current is flowing through the sidewall of this thing. The distance around would be 2 pi r, right? And so that's the distance around from here to right there. The length of this thing is L. So the area is 2 pi RL, right? And so if you go out to a larger shell, let's think, if you go to a larger radius, it should be a little bit easier to flow through because you've got a bigger cross-sectional area. And so, Nick, does that address your question?
Yeah.
As you get to larger radii, each shell it's a little bit easier, right? The current can spread out. A couple of days ago, we talked about current density, and we said, oh, the current density is lower out here. It's just easier for current to flow because it's less dense out there. All right, so in this case, let's try and write down our equation. We know we're going to need calculus. Rho, in this case, I'll still say ds over the area of my shell. The area of this 2 pi RL. Right? Now, ds is supposed to be the length of the shell. And this is where it gets kind of weird. Remember, it's the length through which current passes. So it's this length. Right? For this particular shell, current is flowing that far. What's a good name for that far?
dr.
That's right. What do you think? So far, so good? Now it's just easy. What are the limits of integration?
A and B.
A to B. And so some stuff is constant. In this case, constant, 2 pi or constant. So, and what if this was non-uniform? Well, then you just plug in a number for rho, right? It's not too bad. See if you could beat me to it. Log B over A. And remember, when I say log, I mean natural log, unless otherwise specified. I'll tell you if I mean base 10 or
Yeah,
something.
that threw me off for a little bit.
Yeah, so I can't help it if math people are weird. You know, math, yeah, the math people, they always want you to, yeah, natural log should be log. Yeah, that's what physicists think anyways. All right, so, yep. All right. Believe it or not, I'm not even making this up. Most physicists will say log when they mean natural log. That's not a just me thing. That's almost every book, all right, or person that does physics. So what should we always check? Units. What should be the units of this? What's the units of this function?
None.
No units. What should be the units of the argument of the function?
None. They should cancel.
No units. So this has no units. That way you could punch it into your calculator. This has no units. Still looking good. What are the units of this? Remind me the units of resistivity. You'd better know this after yesterday screwing it up a bunch of times.
Ohms. Meters.
Ohm meters. It is not ohms per meter, right? It's an ohm meter. Okay. Divided by meters. Check. Okay. So the most commonly screwed up units are those. People want to say ohms per meter. We're used to doing ratios like that, but it's just not true. It's ohm meters. Okay. Feeling good. Should we try another one? I say yes. Do you think this would ever be used in the real world? What do you think?
Yep, you're manufacturing resistors.
Sure. This is also used, this particular, you could do the resistance of seawater. So, yeah, it's physics. So no, such a chemistry thing to say. So yeah, but you could actually use this. I believe this is the standard shape they use for measuring the salinity of seawater. So you could tell how much salt is in seawater by doing the following. You stick out 2 metal cylinders and you run a current through the seawater. From that, you know the voltage you applied, you know the current, you know the resistance. From the resistance, you get the resistivity. That tells you the salt content. There's just one application you could think of. And so, yeah, if you needed to find out saltwater concentrations in general. Oh, wait. Are we saying that physicists figured this all out for the chemists? Probably. We do everything for the chemists. You got to teach them something. Somebody had to figure out the periodic table for them. Just getting the chemistry jigs in hard tonight. How many people in this class are chemistry? I don't know. Whatever. It's just good natured. Yeah. Yeah, something like that. You actually don't even need that much current, right? Oh, my bad. Oh, now I'm in trouble. My bad. Sorry about that. All right. Let's get back to doing some physics. So, I'm gonna let you guys try 26.9. Right on. I'm just, I'm teasing. That's why I do it, because I know you can take it. All right. Let's take a look at another one. Let's look at 26.20. I'm gonna let you do 26.19 at home. Let's look at 26.20. All right. And I'll bring it up on screen. So do this one at home. And maybe instead of doing this problem, let's do this, everybody. Look at it and tell me which parts, if any, require calculus and which parts don't. Before you do all the math, do they both require calculus? Does only one? Let's see. Okay, so a trapezoidal piece of metal, constant resistivity, so we don't have to worry about that. Height changes from the left to the right. Okay. The height change is exaggerated. Got it. Okay. So A and B are approximately equal, but B is a little bigger. Determine resistance between the front and back face, and then determine resistance between left and right. What do you think?
Left and right need calculus.
Yeah, exactly. Going from front to back, we do not need calculus, because even though it's a weird shape, the area is constant. So on the top one, it's just rho L over area. So let me be clear. For this part A, it's just rho L over area, and you got to figure that out. And then for part B, we're going to need to do calculus. That's going to be R equals integral of dr shell. All right. So rather than do the entire integral, let's set it up together and then move on to the next problem, because I know you know calculus. Okay. So try and set up part B. And if you finish that early, then set up part A or something, and we'll go on to the next one. And then, yeah. So part B, this is what, 2620. B. D. Okay. Anybody that wants to chime in can. If you want to work on your own, that's cool. I know I need to use this calculus equation. R equals rho ds over the area. So what is any of that? I guess rho, we got that. That's a constant. What is ds? What is area? And what are the limits in this problem? Any thoughts?
DS is probably D, I'm guessing, and area is gonna be what's gonna be integrated.
Okay. You said DS was equal to
The
what?
length, the D.
Ah, no.
Probably.
So this is an infinitesimal length, right? D is macroscopic, so that can't be right. It's got to be a small amount of
Sorry,
length.
I meant D. Yeah, I meant the small D. Del D, whatever you want to call it. I don't know what DD is.
Yeah,
Would it-
that's what
Would it be like D? Would it be
I'm asking. Go ahead. Somebody
DR?
else.
Would it be like DR, and then your bounds of integration would be from 0 to D?
Okay, you're right. So you're both on the right track. Do you agree we have to integrate from 0 to D?
Yeah.
What's a good name for this direction?
X.
So what's a good name for DS?
DX?
DX.
Oh,
Yeah,
okay.
there we go. There we go. Because DD, that doesn't make sense. The derivative of a constant would be 0. So remember that this is some arbitrary piece. Now, it's kind of hard for me to draw this, but you could imagine this is going into the page, right? And so if I could, I'm trying to, oh, this is really hard to draw here, but I can't do this. Yeah.
It's beautiful. You're doing great.
There we go. I'm just going to say that this is basically imagine this is going into the page. This dimension here would be the thickness of that little shell. And the idea is I'm going to add up that one with this one, 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 with this, and grading over X. So that means I better get X involved. That's probably the distance X, right? The distance to this thing. Let's scoot this closer. Whoa, that was a flying, oh man. I got an idea. We'll use this to get, whatever.
Don't leave us suspense. What was it?
Oh, it's the marker cap went flying behind everything I own. It's like deep in the corner now. Whatever. Yeah, that's what I get for, see, this is what you get when you make fun of chemists. You lose your marker caps. All right. Okay, what's the area, people? Help me out. Oh, and you already said the limits were 0 to D, right? There's only one more piece. I'm going to see if I can find that cap while you think about it, okay?
A times D times DX, I think, right, guys?
Well, it's the area of the
Or X, sorry.
Yeah, what are you thinking for? I just found a black cap. That'll work for now. What do you think the area is?
Wouldn't it be the area of a trapezoid, which would be
It's not the area of the trapezoid. We need the area of this. And remember, it's thickness C into the page.
C times Y.
Okay, so C would be the depth. And he says times Y. I don't know who that was, but what is Y?
It starts off as A, and by the end it's B.
Yeah, so it's something that's changing. How is it changing?
We could find the slope of X.
So you just told me Y is equal to slope X plus intercept. Now, I know a lot of you use mx plus b. I hope you agree that's a bad way to write it when b is one of the parameters in our problem. So that's why y, this height here, I don't have anywhere to write it. That height is y, and it's changing. It's some function. And so now you see how these problems get tricky. You have to get your own functions before you can integrate them by looking at geometry. Okay, but now that you know that you have to do that, it won't be quite as bad until you see the next problem and be like, gosh, I know nothing. All right. What's the slope here? Was that Eston that spoke up? Was that you? was that somebody else? I have no idea who it was.
It was Tom.
Is it
Tom.
B over D?
It's not B over
B minus A over
D.
D.
Yeah. Remember, it's rise, which the rise is only this portion of it. You see that? B minus
Yes.
A. Yep. Okay. And what's the intercept here?
A.
Yep. Are you Canadian? Sure thing, eh? Don't you know? All right then. All righty then. I have problems. My Scottish, my attempt at Scottish accent, Canadian, and whatever else. They all sound the same. Bad. All right, so let's take this and shove this into here. Actually, let's not. This is a trick. I know this is going to seem a little bit strange, but I just want to try something. I'm going to take the derivative of this equation before I, what? Watch. I want to just see what happens if I take the derivative of this equation. Don't I get dy dx is equal to b minus a over d?
Yeah.
And can't that be rearranged? I don't like doing this. When I say take the derivative of this, I'm going to keep the dx over here. So basically cross multiply by dx, right? That's just saying, okay, if this is a derivative, these are constants, that's a derivative. All right, got it. I know that's sloppy, whatever. But in this case, I'm going to flip this around a little bit. So I think dx is equal to d over b minus a dy, right? Why did I do that?
So you can keep A on there with just CY.
If I plug this in for dx, this is cy. It's an easier integral to do. And we're right back to our logarithm, right? And so that saves you a u sub. Now, this trick doesn't always work, but I've seen it work for more than 3/4 of these resistance problems. So for some reason, because of the way these are formulated, it very often works out that if you figure out this function of y here, and then actually figure out dx and plug in what dx is, now you got to be careful. I'll show you what I mean. All right. This is a physics class, not a math class. So let's make sure we do this right. All right. Today is the arrogant physicist day. All right. In this case, I still have rho. I'm going to plug in and I'm going to shift my dx to dy using d minus b over a dy. On the bottom, my area is c times y. And that's an easy integral, right? What are the limits again?
0 to
No.
0 and D.
No.
No.
We're now doing a y integral.
Oh, that's right. It's A and B then. Yeah.
Yeah, you like that? Isn't that fun? There must have been some special sauce in that green tea tonight. I'm having a lot of fun. I don't know why. That's a way to do it. What do you think?
Try not to.
This is easy now, right? Just yeah, try not to think. Yeah, right on. This tea is good. That'll keep me going for the rest of the day. All right. Let's take a look at the solution and see if there's something else there or something. But it's now you know really what the heart of these problems is. In these problems, what do you have to do? You have to get to your integral, right? The rest of it's easy. But figuring out how to get to the integral is no joke. One, you have to think in 3 dimensions here because the thickness is an integral part of this slice every time. And having to figure out that what is the thickness, what is the length is not easy every time. So that's one thing. 2, sometimes you have to use a function. You have to use a curve from the shape itself to figure out the area. If the area is changing, it's changing based off geometry. You have to use your math skills to figure that out. Finally, this is a trick that could dramatically simplify your work. It basically prevents you from doing a use. I don't know. Use subs aren't that hard. So whatever. You don't need this trick if you don't like it. Okay. So expect something on your quiz where you have to do this kind of stuff. And it's really easy to make different versions, right? Really easy. All right. So there's a lot of different versions of stuff like this. You could do parabolas, you could do cubic function, any polynomial, you could do sine or a cosine, you could do all kinds of different shapes. And so, and then another thing that you could do is you could switch around the letters A, B, C, and D, right? And so then it's really like, and one of the things that you also need to do is you're always thinking about, whether I'm going right to left or front to back. So you want to be thinking about how those factors affect it. And these things all relate to our fundamental equation, R equals resistivity. So resistance equals resistivity times length over area. So it's just a different way of doing that. Now let's look at that solution and see if there's any nuggets. What problem was this? Oh man, that's a long resistor. Look at that. All right, so, that was those. If you guys haven't watched this video, it's a short video. This video is worth watching after class when you get to there. It's kind of fun. It's only like a minute long and you get to see you get to see me spaz out a little bit. All right, there's some boring stuff. Oh yeah, gosh, we've covered a lot already today. Sorry about that. All right, so that was the previous one, wasn't it? There we go. So maybe this kind of helps you see that a little better. My apologies if it's not perfect here. This is kind of good. Hey, this is something I forgot to tell you that I almost always check. Remember when we wrote this line? Usually I remember to do this. Anytime I write a line function, I usually try to remember to check it works by plugging in the two endpoints. Why not do that one simple check before you go on? So when you do this, if you plug in 0 here, you get A, right? If you plug in 0 for X, you get A. If you plug in D, you get B. So it looks good. All right, and then here's this integral. You could have done this integral. And then here's the weird trick. Instead of doing a U sub, I do this, which we discussed about. Oops. So zoom. And notice we get that other log integral there. Yeah, get the same thing. So it looks like there's not much else to say there. All right, so let's go on. Let's go back to here. Let's do one more of these and just see here. So 26.21. And then after this one, okay. Here's a parabolic version, right? Another way you could mix this up that's really easy, just make the resistivity as some function as well, right? Okay. Suppose now that the height was varying parabolically, parabola's minimum occurs at the left face. Okay, I'm gonna write this shit down. $26.21. Normally when I have class, I have pieces of foam I can show you, but I didn't think to gather those. If you remember from the center of mass day, you might remember a piece of foam that looked like this. That was a, oh, wait, you guys didn't, we did that all online. Oh, well, never mind. Yeah, it's fine. You're still learning something. All right. So you've had a second to look at this. Any ideas how to get that height function? Hopefully you didn't look at the solutions, but if you did, that's fine too. I don't care. That's what
Yeah,
they're
I got
for.
a
But
formula.
sorry, go ahead. I couldn't hear you.
I got
I guess good.
you know the base function is y equals something x squared plus a.
That's good. How did you know that?
It's just the
You got,
you know what, x equals 0, y equals a, right?
yeah, you know, this is if it goes at the origin, and then you said you shifted it up, right?
You know when x equals d, y equals b, so that you can solve for
Yep.
that something.
This is good. I would like to generalize this first, though. Can I write? Yes, very good. So let me catch up and write this way. Y equals, I'm going to call this constant 0 plus constant 1 times x plus constant 2 times x squared. And our goal is to now figure out these three constants. I think I might have used the letter K in the solution. Let me see if I used the letter K. I did. So let me switch these C's to K's, okay? And then I'm going to get to where you did first by saying, this is a general form of a parabola, right? It's a polynomial of order 2. And what he said was, if y equals 0, or wait, if x equals 0, we need this to be true. Or I guess we require, right? The idea is if you set x equal to 0, we know the height should be a. And so, well, look at this. Doesn't that tell you if you have this, a is equal to k naught plus 0 plus 0. It says that k naught is a, which is basically what he just said. He said that plus term had to be a. So if you didn't see that with intuition or something, that's how you could do this. And this general procedure would work even if it's a different parabola or any arbitrary curve, okay? So there's that. Now, we also know, I think this is what you were saying, and I think you were saying if x equals d, y should equal b, right?
Yeah.
And if we plug that in, now we know that this one is a. K2b squared. I don't know these two. So I need one more piece of information. What is that? How did he figure out that? I mean, he used intuition to get K1 is equal to 0. How can we find that in general? Is there anything else we know about this function? We know its height here, and we know its height there. What does the minima tell us? You know, it's a minimum at the origin, right?
That's an even function.
Yeah, if it were linear, then it would drop off to the left, and
How do you get a minima in calculus?
Derivative equals 0.
Derivative equals 0 at the origin. We know y prime, which is equal to K1 plus 2 K2x equals 0 if x equals 0. That's what the words told us. And notice, if you stick in x equals 0, doesn't that tell us that K1 equals 0? It does. And so he was doing that all in his head, I think, basically, somehow, which is cool. But notice, oh, whoops, if x was equal to d, oh, I plugged in the wrong symbols here, didn't I?
Yeah.
I'm sorry. That should
be
be D and D, shouldn't it? And this should be B. So if x is equal to D right there and right there, we'd expect that y is equal to B. Right there. Gosh, good thing there's the solutions. You might want to redo this one later, but just because I kind of slopped that up a bit. But yeah, now after this, isn't the problem exactly the same as the previous one? All right.
Do we need K2 as well?
So I don't know. Go ahead. Question.
Yeah, do we need K2?
Oh yeah, K2 you could solve. We could see that K2 is going to be B minus A over D squared. Right. Solve this. This drops out. You get B minus.
Okay.
Yep. And so that tells us that this is going to be. You could check the units. And before you go on, what's something you might want to do with this equation to check it? Plug in the two endpoints and make sure you didn't just screw up something accidentally, right? So if you plug in x equals 0, this drops out, we get A. If you plug in x equals D, the D squared drops out, you get B minus A, the A drops out, you get B. So it looks plausible. It obeys the minima at the 0. This, yeah, so try to do something. In general, imagine you're a civil engineer shaping concrete for some weird Guggenheim museum or something else or whatever. You never know what you might need a curved ramp of concrete for, right? Something you could do is you'd say, all right, well, I want this curve and I want the minima here. So I was trying to think of something that might be somewhat plausible. What if you need to make a parabolic mirror and you need to know the shape? This would give you a general way to make a parabolic shape. So don't forget that you can go back to just making a power series, right? That's what this is. It's a 3-term power series, x to the 0, x to the 1, x squared, and then just figure out the coefficients. Or you could plug in some numbers in Excel and just change them until the curve fits what it looks like. You could take a picture in the real world and then just plot out points and then stick it in Excel and do a curve line fit. You got it. All right. So curved surfaces, not everything's linear. That's how you would handle a curved surface. What do you think? This is a lot of stuff today already. Let me just see where you're at. Is this getting a little easier? Maybe? Somewhat? Maybe still need to do a couple more, right?
It's mostly just like noticing the 1 or 2 things you could forget per problem.
Yeah. So on your quiz, you're probably going to get some stuff that has resistivity. You're probably going to have something with calculus like this. Let's see. You probably have something with temperature, right? And there's probably something with plots. So that sounds like a typical quiz for me, right? Something with a plot. And then we did temperature, we did some calculus. So basically, make sure you know this chapter inside and out. And hopefully the plotting part, at least, after you do the questions in the workbook and did this really long lab, geez, you better be good at that, okay? So the overwhelming majority of you should do pretty well on that question, unless you have some, brain fart on that quiz day, which happens sometimes. All right. Let's take our break right now, and we'll pick it back up at 5:45, okay? Unless you have any other questions. You can take your break now if you don't have questions.
This might be kind of a dumb one again, but when you got your slope for the first question,
It's lagging.
sorry. When you got your slope for the first question,
Yeah.
it was B minus A over D all times X.
Yeah.
Can you just like briefly explain where why the x was a part of that? Because slope is just rise over run,
Yeah,
which
yeah,
is what we had with the b minus a over d.
right. Was this 26.20?
Yeah.
Okay. If I come out here some distance x, this height right here, I'm calling y, right? And we see that y is equal to I am assuming this is a straight line. This is the equation of the straight line, and I just need to find the slope and the intercept. Are you okay with that,
Oh,
Ryan?
okay. Yeah,
then
so
in
the
this
x is just kind of
case-
in the equation.
Yeah,
Okay.
that's the definition of the linear equation, right? So it's slope.
Right.
Yeah, so you're probably used to saying y equals mx plus b, right? That's what we usually say. But that's
Okay.
slope times x plus intercept. And so I write out the words just because I'm always paranoid about m being meters or mass or b
Yeah.
being, in this case, blah, blah, blah. And so rise was b minus a, run was d. And then from there,
Gotcha.
I think you're good, right?
Yeah. Yeah. Yeah.
All right, cool. Yep. And so it's just from that stock equation. Good question. All right, I'll take a quick break and be right back. I'm just updating a link in the chapter 26 solutions really quick. All right. So hopefully that's uploading right now as we speak. So if you've got the chapter 26 solutions open online, you might refresh those. So sometimes the links that I posted when I convert the PDFs, they don't process properly. So I put the link in there. But I'll share screen. And here's a little puzzle that I made for you guys. Okay. So
Professor, we can't hear that.
oh, you can't hear it?
No.
All right. I tell you what I'll do. Whoa, that's weird that I don't. Okay, hold on. Give me a second. All right. I suppose I could turn the volume down on the video and just explain it. How about
There
that?
should be a button when you
Yeah.
press screen share. It
To
should
share the
say
sound
share
too?
computer sound.
Ah, okay. Well, that's fine. I tell you what, why don't we open up to page 113 on the workbook and look at questions 26.22 and so you're right. We'll figure that out later, but this is the fun part. All right. So so let's share that screen first. All right. Yeah. My bad. I didn't select that button. I see the button there too. It's just, yeah, whatever. How does the video come through when I'm playing a video off YouTube through my Zoom to back to YouTube? Does it lag?
Horribly.
It's pretty bad.
Plays about at like 2 FPS.
Yeah, so I linked this. This is the video I linked. So it's linked in the solution, so you can watch the video at your leisure at home. So that's probably better anyways. How about the simulations that I show? Do those turn out okay sometimes or not?
It's
When
usually
things
pretty
are
okay.
moving, it's a little bad, but you know,
Better than the video,
yeah.
Yeah,
but still
solutions are
not great.
a lot better than the video. In my
Yeah.
opinion.
All right. Yeah. All right. So anyways, yeah. Okay. So that said, I tell you what I'll do is I'll let you guys do this at home and you can watch the video. But this is like a fun little puzzle. It's actually got a video. I linked the video in the solution. If the video link doesn't work, just hit refresh on the solutions and you can do that. So we're done with this chapter now. Yay. And I definitely think you'll enjoy that one. It's just a fun problem. So you could do the rest of the problems on your own at this point. And we're actually, that problem was supposed to be a segue. So maybe I'll just share the screen and just mention this. you might notice that these light bulbs, I don't know if you can see this or not, but these are in parallel, right? Do you see that? So these light bulbs are in parallel. Okay. Then later on okay. Notice that these light bulbs over here are in series. And so this is usually a lot more fun when we do it live in class, and you could try and predict what should happen, pause the video and think, which one should be brighter, think it through. And then you play it out. And so this was supposed to motivate. We need to understand series and parallel for resistors. We've danced around this several times. We had a resistivity question that had it. In the lab yesterday, we needed it. We need to really understand series and parallel rules, and this was supposed to motivate that. So, okay, that said, let's look at those rules. Okay, that's all you really needed to get out of that demo. It's super fun, though. Why didn't it clear? There it goes. All right, so let's get back to this. Okay, blah, blah, blah. And there's another, this is a weird little one. This relates to that I was talking about earlier about the ion concentration and resistivity. So that's in there for you too later. All right. Hey. All right, so this chapter is a big one. The math isn't that hard, but there's just a lot of stuff in it. Everything in here you've pretty much seen before at some point. But I guarantee there's going to be some steps that are tricky, so we got to practice. All right, so before we talked about parallel resistors and parallel capacitors and series capacitors. Now we've got resistors, okay? Hopefully I remember to update that. I need to fix this word down here. That should be, yeah, okay, whatever. That should be current, and I need to fix that line. This is page 117. Okay. All right. So the big thing I want to point out is this. In parallel, resistors do the 1 over. In series, resistors, you just add them up. For capacitors, the rules for that particular thing, for equivalent capacitance, were flipped. Now, the voltages still add up to the total, and the currents are equal. So these two rules down here are effectively the same as capacitors, okay? This rule is not the same. And I think we were talking about this with Jay earlier in the week, maybe, or a month ago or sometime. Okay. Now, if you have things in parallel, their voltage are the same and their currents add up. So this is something you've got to get down for resistors and capacitors. How I remember it is for capacitors, Q's were equal, right? And the definition of current is dQ dt. If you have the same current, you're going to have the same derivative. You get the same currents in series. You get the same charge in series. In voltage, things have the same, in parallel, things have the same voltage. The currents add up. And just like before, the power delivered, they add up to the equivalent. And now we have poison ivy and Ohm's law. Before we had U equals 1/2 Q delta V. Now we have power is just IV. Remember that, maybe you know this, what's the derivative of energy?
Force.
What's that?
Force.
Nope. Oh, respect to time here. So remember, you might be thinking U is equal to dF dx, right? So energy is the integral of force.
Is it power?
Yeah, what are the units?
Watt.
What? That's my joke. I had to get that in somehow. All right, but notice, so bad, but I just want to point out, if you put in a DI, or sorry, a dQ dt right here, it does make sense. You're instead of having voltage, which is energy, you get the derivative. Well, that should have the units of power, and so this seems totally plausible. So if you check the units, that's, yeah, watts. All right, so basically no 1/2 on this equation though, all right? Now, I've seen this a million frickin' times, and you guys are probably pretty good at it after yesterday's lab. I hope you realize that the voltage across the battery and the voltage across a particular resistor are not always the same, right? So as long as you know that, please, 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 the most common mistake is people always shove in, oh, I'll just stick an E of the battery here. That's true for an all parallel circuit, but no other circuit works that way. So terrible idea to think that way in general. Let's get to this and start working. Now, I think this one, oh, we need chapter 27 solutions now. So I'm going to open that up. Hey, I actually remembered this one. So I haven't had the time to fix up all the alignments, but you can maybe, yeah, you can see it's not perfect. But so in this one, I'm going to work it out on the board. If you want to, the idea with this one is you follow the red arrows and you get the equivalent resistances going down. And then once you get down to here, that resistor is in parallel with the battery. They have the same voltage. Then you get all this stuff. And then you do the blue arrows going back up. So on this page of the solutions, first do all the red arrows, then go back and do all the blue stuff, okay? So I'm gonna try and follow that on the whiteboard, and I'm gonna, yeah, so this one I actually remember to do. Let me get back to the problem. There we go. So this is what we're gonna try and do. And at this point, if you're good with series and parallel rules and you don't want to sit here through this lecture because you did this in high school and you think you're good at it, that's fine with me. All I ask is that why don't you work on the problems for the rest of this 37 minutes or whatever, 38 minutes. And you don't have to be on Zoom if you don't want to, okay? But if, yeah, so if you think you could do this, great. Or just hit the mute button and stick around until I yell at you, okay? This is what, 27.0. Nah, I don't have room for this problem number even. Oh, shoot, there's another one up here. A 5 and a 15 ohms. And a 30 ohms. Okay. All right. And so when I'm doing this, the first step should be combine which two? Oh, whoops. Let me get this screen share done.
The top two?
Yeah, exactly. So we're thinking these two, and they are in series or parallel.
Series. So
And what do you get when you combine those two?
20 ohms.
20. Yep, you just add them up in series, right? So then again, if you have any, so everybody, some people are seeing this for the first time and never have done this ever, right? So if you're one of those people, try not to be shy. I could care less about people that have seen this already because they know how to do it. So if you have questions, if I'm going too fast, slow me down, all right? But I'm saying that these two are in series, they add up to 20, and so I'm just going to do that step. All right. And you've got the solutions if you are one of those people that knows it, has done this in high school physics or something. You can use the solution and make sure you know what you're doing. That's cool. I don't know which way the battery was pointing. Doesn't really matter, right? The current would just flow the other way if I flipped the polarity of the battery, but. All right, so that was a series, right? So what's the next step? Somebody else.
Add up the ones in parallel, or not
Yep.
add them, but use the relevant equation.
Right, right. And so what is that going to be?
It's the 1 over equation, right?
Yeah, the 1 over equation, which we could use
Which
the
is
shortcut as
equivalent
well.
to, yeah.
Yep. And so that's going to be over 50. What is that, 12?
Yeah.
Okay. Okay. And as you probably figured out by now, it doesn't really matter how you draw it, right? So if I make this a long, skinny circuit to fit on my whiteboard, that's okay. All right, and there's still a little glare. That's all right. And so now these are in series. I just add them up. All right, and so I've worked my way down. Oh, and I should write that that was series combination. And so once I get to this final stage, why is it useful to do all this? Why is that good? What's the piece of information we now know about this resistor?
The current.
Okay, but first we know what?
The voltage across it.
The voltage, which helps us get the current. So you're right. Both of you are good. So, but here, if I know this is a 1.5 volt battery, I know that this is going to be 1.5 volts. Maybe I should do this in purple just because that's closer to blue. So now I know this is 1.5 volts, and from that, I could get the current. And then I need to see what that number is really quick. Looks like I got 41.67 milliamps. And hopefully that's what you got as well. All right. Oh, let me get this out of here. What do you think? So that's phase one. Get down to one resistor. Why? Because then we know the voltage here is the same as the voltage of the battery. Because when you have just one circuit element with a battery, we know this has to have all the voltage of the battery. That's why we do that. Then we're going to start working our way back. What do I bring back with me? What do they have in common when they're in series?
Current.
Current. So now I know this is 41 points. Whoops. Now I know both of those, and I'm going to scoot this just a little closer so it's not so small. Now that we're done with the bottom one, now I can get it a little closer so I could see better. All right, and so at this point, you could get the voltage pretty easily, right? Because well, I know the resistance and the current, Ohm's law, V equals IR. So I should be clear here. If you weren't sure what I did to get the current here, I should make sure I did I is equal to delta V over R. That's how I got this current right there. So again, to get this current right here, I took this voltage and this resistance and used that equation. Now I'm just going to use V equals IR. I know I in here. So here I'm going to use delta V equals IR on these two. And I'm just going to read the numbers off my chart and you can double check them.
Maybe I'm doing something wrong, but I'm not getting the same number as you, the 41.67. You said just divided 1.5 divided by 36?
Yeah.
Milliamps.
Oh, milliamps.
The decimal.
Oh, okay. Yeah, okay. I see it.
Is that what it was? Oh,
Yeah.
millis.
Yeah, I got you.
Yep. Okay. Yep. Cool. And then notice the energy or the power, I did milliwatts as well. How do you get the power? Poison ivy, right? I lost my numbers already. I'm losing it. So, where's Zoom? So many windows. Everybody, you know how it is. So if I wanted to get the power, remember, I could always use poison. Resistivity? No. Power equals I times delta V. And you could use Ohm's law in here. It's also I squared R, or it's also delta V squared over R. But if you wanted to get the power, you could do that as well. More on that later. I don't have enough room here. But so basically every time when you go back, you're either going to use V equals IR or I equals V over R. And then you can get the power using V squared over R or I squared R or IV. Okay. And so when you do that, I'm more interested in what do you bring back each time. So let me get the voltages here really quick. Whoops. I got 0.5 and 1. Okay. Where's Zoom? There it is. All right. And so I just got that number. And so that's looking good. Again, with the millis, watch out. So now let's think, does this make sense? In series, two resistors have the same current. And I know Ohm's law is this, shouldn't the larger resistor have more voltage in series? And it does. So this is the purpose behind having nichrome wire. You could put a heating element and it's got a high resistivity. So it'll get most of the voltage. It'll have the same current. And so that will be the piece of the circuit maybe that gets hot. I don't know. We could see. More on that later. All right. I should be careful because let's just ignore everything I just said. You got to be careful sometimes. So let's go here. What do we bring back now? In this case, this one's done, right? We've already finished it down here. So this one up here, we need to share the voltage. So both of these have 0.5 volts. And then you would get the currents. And I think from there, I don't know. Yeah. All right. We'll do one more line. We're almost done. So the currents are 25 and 16. Yeah, we should do this. Yes, this is a good, important step right here. I'm glad I didn't stop. All right. There's a very common mistake students say all the time. It's a very common misnomer, and it's addressed at this moment. So there, I got the voltages and I got the two currents. I think you have probably heard the phrase, current takes the path of least resistance, right? You've probably all heard that. Well, guess what? It also takes the other path too, just not as much. So students sometimes will think, oh, this is the smaller resistor. All of the current goes that way. No, only some of it, right? So watch out. You could imagine if these two were equal, you'd expect exactly the same amount. This is how you could check your work. The smaller resistor should have more of the current. And there's a little numerical thing. Look, you got 20 ohms and 50. So you have 20 ohms and 30 ohms, right? In theory, you could think of this as being 2/5 of the total possible resistance 3/5. So we'd expect the currents to be in the ratio of what, 3/5 and 2/5. So this should be 3/5 of the current, and this should be 2/5 of it, right? If this is 2/5 of 50 ohms, it has 3/5 of the current. If this is 3/5 of 50 ohms, it has 2/5 of the current. So if you want that little shortcut, great. But just this is really what you should know. More of the current takes the path of lesser resistance. That is a more accurate statement, and that is useful. And then from here, these two have the same current, and you're done. Let's see. How did you do? Are people getting this at all, or not? The series parallel rules. I hope this makes a little more sense than the capacitor ones, just because you've been doing it for a while now, right? Hopefully when you go back and look at capacitors just to review for the final, it'll be easier as well. So, all right.
It's like really similar to capacitors.
Yeah, the what you bring back is the same. The only difference is watch the rules. And if you don't remember, on the back of your equation sheet, you could just literally write it down on there, right? So some of these rules are somewhere. You can see, oh, well, there they are right there. And I've got them lined up. So this looks like the series and this looks like the parallel. So if you want, you could write parallel next to those and series next to those if you have an equation sheet you work from. All right. All right. And then, all right. Let's take
I
a
have
look.
quick question.
Oh, yeah, go for it.
I don't know, maybe this is something you plan to do later, like you did with capacitors, but is there a way you can explain kind of conceptually why resistors in parallel use the 1/over rule? Because it kind of makes sense to me why you would use to just add them up in series. And there was the whole way you explained capacitors to us, you know, you know, physically how they, yeah.
I think it's kind of the same way.
It is similar, but the equation's flipped. We know resistance equals rho L over area, right? If you put, now let's just make this simple and assume that they have two identical resistors, okay? Identical in every way, just so I don't have to think too much. If I put these two in parallel, isn't that effectively like doubling the area? Think about this. If you had a wire up here like this, and you put another wire right here like this, if you put them in parallel, you double the area. It should be easier for current to flow, right? You've got more area for the charges to flow through. That's
right, okay.
And so now I'd see that R, the area is on the bottom. That's why I get the 1/over rule.
Okay, yeah.
Right? And now if I do these end to end, isn't that the same as the nichrome wire that we just did with the copper or whatever, or carbon or something? I'm doubling the length. Length is in the numerator.
Right. Okay, cool.
Is that helping?
Yeah, definitely. I'm remembering that now. You did go over that, yeah.
And then don't forget the capacitance. Because this has area in the top and length in the bottom, that's why those rules end up being flipped compared to the resistor.
Gotcha, yeah.
All right. Yep, good question. And I think for me, I know that seems crazy, but that actually helps me remember the rule because I hate trying to memorize stuff. So
yeah, definitely.
Yeah, if that helps you remember it, that's great. Okay. Now, let's take a look at some of these things next. This one. All right. Now, you could start to fly through these, and it's going to seem pretty easy at first, but I want it to feel a little bit easy just so you can get used to using this. This is not epsilon, it's script E for EMF, electromotive force. That's a capital E in the symbol font or in the script font. All right. So if you're in, yeah, whatever. Okay, so in this case, let's just look at this one. We're going to try and get used to doing these algebraically because that's how I like to put them on tests and quizzes, and I think it's good for design work too. So, right, let's not overthink this. This is a little bit faster way to draw a power supply for right now. Okay, so this is 27.1. Circuit 1. Normally in class, I have a bunch of light bulbs and switches and we could play with them. Well, welcome to ERT mode. Yay. All right. So in this case, I know that delta V of this resistor is E. E. And then I know the current of this through this resistor would be, so this is the voltage across is E. The current through is delta V R divided by R, which in this case happens to be E over R. And the power would be, you could say it's I times delta V. Another way is I squared times R. Another way would be delta V squared over R. Either one of these, any one of these gives you the same result. It's going to be E squared over R. And so the merits in doing this simple problem and working this out is you can kind of see when we're doing algebraic problems now, you expect voltages to be fractions times E, currents to be fractions times E over R, and powers to be fractions times E squared over R. All right. So that's circuit 1. I'm going to start flying through this. Okay. So if I'm going too fast, you let me know or go to the live stream and slow it down. All right. In this case, we're going to look at another one of these, circuit 2. Don't overthink it. What's this equivalent to? If this is R and this is R, what's the equivalent resistance? It's in series.
2R.
2R. You just add them up. Okay, so now my voltage should be E still. My current should be E over 2R in this case. And the power is going to be, let's see, IV, E squared over 2R. There's a reason to do this problem, but I hope I'm not going too fast. Again, we found the equivalent resistance. Once I know that, I know this voltage has to be that voltage. And then, okay, now I get the current from voltage over resistance and the power. So this was delta V over R, and this was I delta V. Okay, that's how I got those. What do I bring back? What do these each have in common with the equivalent circuit?
Same current.
Same current. So what does that mean the voltage is on each of these? E over 2. We see if you have two identical resistors, they're going to have the same current, which is exactly half the previous current, right? And I see that they split up the voltage equally. And then the power, more power, I'm going to get, ooh, a 1/4 E squared over R. And finally, we could talk about this power a little bit. It turns out the brightness of a bulb is most proportional to power, not current, right? The brightness has to do with energy per unit time. And so we see that when you put two light bulbs in series, it's not half as bright. It's 1/4 as bright. And that's something I wanted to point out here. Okay. They each get half the current, but they also each have half the voltage as well. This is a script P. Yeah. So to make my P's like this, I just do a bubbly P. Yeah.
Is there like a subscript that we could do, like P subscript something? Like
Slash
P subscript.
Script P.
I'm saying just like when we're writing it down, because
Oh.
I'm like,
You just You could do, how about this? Just capital P.
Capital P. Okay.
Yeah. Yeah, it doesn't matter. So I just try to keep my P's all looking different because this for me is pressure and lowercase p, and then there's rho. It's like,
Okay.
that's all I'm saying, you know. Just, yeah, you could do this. Except then I just do whatever you got to do. This is totally fine. The context should make it clear. You'll know if you're doing a power problem versus a pressure problem usually until the end of the semester. Because then we use momentum, power, and pressure all in the same problem. Whatever. All right. So yeah, great. That's problem 2. All right. Now here's the deal. What's going to happen if you put a switch here and open it? Oh, wait, there's an open switch. What's going to happen here if you close this switch?
It'll bypass that second resistor.
Exactly. And so here, if this is a resistor with say 10 ohms, and this is a wire with less than an ohm, almost all the current will go this way, right? So if you have the current here flowing through, most of the current is going to go this way. A tiny trickle might go this way. Remember, most of the current takes the path of lesser resistance. So there might still be a millionth of an amp this way, but overwhelmingly it's going to go this way. And so if you put this switch in here, this current drops to 0, we get back to circuit 1, right? So this would take all the voltage, this would go back up. So if you put this switch in there and short circuit this resistor, that's what we would expect. We get back to our original circuit. So this would be a way you could turn it on and off and make this be 1 bulb full brightness or 2 bulbs at 1/4 brightness. All right, cool.
It's like making a pull down resistor.
What's that?
Like making a pull down resistor. It still works if it's in the series of the resistance is high enough.
Yeah, I was having a little trouble hearing the end of your sentence there, but yeah,
it's like a pull down resistor and electronic, so it drains off power.
Right.
Don't do anymore.
Yeah, totally. All right, cool. Sorry, I'm like looking at the clock. If my apologies if I'm not, but I agree with you. I'm just trying to get through as much as I can to give you a jump on the weekend. Okay, we've got R, the equivalent circuit here. I bet you could figure this out. What's the equivalent resistance when I put 2 resistor R's in parallel?
1/2 R.
Yeah, R over 2, because it's R times R over R plus R. Nice. And so here I get more current. I get the current is now 2E over R, because it's E divided by R over 2, the 2 flips up. And the power is going to be twice E squared over R. So notice it's not exactly the same as the previous problem. When I go back up here, these each have the same what as the equivalent? I guess it's pretty obvious.
Voltage.
Yeah, I'm holding the green marker. Yeah, so right? And notice, think about these nodes, right? If you think about this, everywhere down here would be at 0 volts. Everywhere up here would be at E volts. And so clearly the difference, the change in voltage is E across both of those. All right, and so next, the current would be and the power would be E squared over R. Wait a minute. Wait a minute. Isn't this exactly the same as circuit 1 for each individual resistor? If you compare this to circuit 1 on this page, this is exactly the same for each individual resistor. But the total power is twice as big. What gives? The battery has to push twice as much current. And half of it goes this way and half of it goes that way. That makes sense because there's two paths now and they're of equal size, so I get equal current. So can you think of any practical application of this one?
Christmas light.
Christmas lights, what else? It starts with every and ends with frickin' thing in your house. You got it. Everything in your house is wired in parallel like this. Why? I can turn off this switch. This one goes off. This one doesn't get screwed up. I can turn it back on. This is how your house is wired in parallel, right? Now, there might be exceptions, right? Maybe you have certain things in series in your house, but in general, this is a very useful trick. You wire everything in your house in parallel so that you can turn them on and off, and this one will turn off if you break it, and this one is unaffected. Now, if you've ever actually looked carefully at your lights when you turn on and off, say something like a vacuum cleaner or something that's very high wattage or very high current, every once in a while you might notice a flicker of your lights. But in general, that's a transient effect. You might see it dim for just a half a second. And that relates to the wires are not zero resistance and blah, 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 blah. And real circuits are tricky. But for the most part, in steady state operation, we expect no difference when you open and close this switch other than a brief transitory flicker as it reaches steady state. Steady state just means not changing anymore. All right, what do you think about that? So far, so good? I think that's really cool. Yeah.
Yeah, that happens very noticeably when the hot tub turns on.
Oh, party at Ryan's house. Let's go.
Bet, I'm down.
Just socially distant.
Yeah. Hey.
Ryan gets the hot tub and we all get to stare at him from 6 feet away. All right. Yeah, that's cool. All right. So now how are we going to use this crap and how might you be quizzed on this? This probably seems pretty easy. You're probably thinking, dude, he's not going to stick. You're right. I'm not sticking this on the test. So let's see how I might stick this on the test. Ooh. Look at question 27.4, the next one. It's a small variation. Ah, that was it already. Whoops. Oh, and this, oh, I see. I didn't do all of these problems. Notice this. This is what I typically do on a test question. I'll say, by what factor does it change? All right. And so you're either going to say bulb turns off or it doesn't change or the brightness changes by a factor of 4. So if we go back to this one, I think we saw that circuit 2, the brightness changed by a factor of 4, not 1/4, because it got brighter. Okay. And so in this one, there was no change. But let's do one of these down here that looks nasty. I'm going to let you try 27.4 at home. And you could do this. And while so maybe try 27.5 right now. So the idea is all you have to do, it's a lot like the dielectric in-outs or the capacitor flipper things. The idea here is do the entire problem with the switch closed, then do the entire problem with the switch open, and you compare the two and take ratios. That's it. Okay. So why don't you compare this one initially closed to then open. And anytime you open the switch, you have to think, is that a short circuit or does it take something out of the circuit? If it breaks the pipe, then it takes it out of the circuit. If it creates an extra pipe that's just a bare wire, that's a short circuit and that takes that resistor out as well. Let me show you that on the board here. just to make sure before I. Let me make sure. So how do switches work, basically, is what I'm saying. So just to be clear, I know what I was saying. I know you're probably getting really tired and burned out. So in this case, the red switch, if you open and close the red switch, that would bring this, if it's closed, this resistor would be in the circuit. And if it's open, obviously it's not. And now with this one, you got to be careful. If you close this switch, that takes it out. If you open it, it brings it back in. And so this is some kind of a bypass there. All right. And so you just have to watch out for your circuits. If you have this kind of circuit, you could, yeah, anyway, so I'll leave it at that. Go ahead.
So the blue resistor.
The what?
Go.
No, go ahead, Ryan. You were talking.
Okay, I was just gonna say, so the blue resistor is attached on the top.
Yeah. Sorry, I smudged it a little bit.
Yeah, no worries.
Yep.
My question is, you called that a bypass, but we're still talking
Short
about
circuit.
when it's closed, or I'm sorry, yes,
If
when
you
it's
close
closed.
this, you make a short circuit. Or yeah. Is that good, Nick, or no?
Yeah, no, that's
Okay. Hey, everybody, why is this purple switch an extremely stupid idea to build in the real world?
Nothing like having just a short circuit kill switch like
Let's think. If you closed this, let's close the red one too. If you close this, how much current is going to flow through the circuit? Well, let's just think. Current's going to flow. Some is going to go through each branch. Which branch is easiest to flow through?
the one with
The
no
one without the resistor.
Yeah. Now this has very, very small amounts of resistance. And so the amount of current through here will be a trifle, and here will be massive amount of current. And so this will light on fire. That's why you wouldn't want to do this. All right. So yeah. So a trick that you could do is you could always, now keep in mind, every battery has a small bit of resistance, but yeah, you might make your battery explode too. And then you get acid all over your face. And I don't know, let's try not to do this circuit today. One of the links in that last chapter shows you what happens if you apply too much voltage, right? It just burns out the wire and explodes or whatever. It's kind of fun. All right. And while you're doing that, I'm going to try and get something for you ready, okay? So I just put a quick simulation in here. If you guys want, you could check your logic with the simulation. It's not too bad. And you could build your own circuits like this. It doesn't take too long. I think that was, so I'm looking at 27.5, right? So there's 27.5. And this is a really cool one. If you close this, you could think what should happen. Oh. And I don't know if you see that. If you watch the brightnesses, isn't that kind of crazy? So when it's open, you have two bulbs equally bright. When you close it, one of them gets dimmer and one of them gets brighter. And so you could see that this is a Pandora's box of delight that's about to come hit you in the resistor chapter. All right, so you could check what these powers are and these voltages, and you can do that. And even though we can't do this in the real world, they have this nice non-contact ammeter. So the idea is they somehow magically do this. All right, and so you can see what happens to the current in each branch. Those are equal. And then these two, the currents should add together. So if this one's at 0.3 and this one's at 0.3, hopefully the net current is 0.6. There it is. And these kinds of, and so you can get a better feeling for these by building these and playing around with it. And so I'm going to stop the live stream now.